Hello everyone. In this video we're going to look at this question. I have a gear or a pair of gears and I have selected them to transfer a power P or H, whatever you want to call it, from one shaft to another while the shafts are rotating at RPMs like N1 and N2, or in this picture N2 and N3. Right? So you want to transfer some rotational power from one shaft to the other while they are rotating at so much of RPM, or radians per second, rotational velocities. And you want to know whether the gears that you have selected, whether the tooth of these gears will tolerate the load on them or they will break, right? Whether you have selected the right gear. So here, let's talk about that. So here you can see two gears. You might call them gears 2 and 3, or 1 and 2, doesn't matter. And each one of them, they're external spool gears. By the way, all we're going to talk about is the spool gears right now. We're not going to talk about helical or worm gears or anything, which are more complicated. So we're going to just talk about the spool gears. And I assume that you know basic geometries of the gears. You know about the pitch circle, you know about the pressure angle phi, and so on. So I'm not going to talk about them. And the RPMs are N2 and N3 in radians, in revolutions per minute. And here is the force diagram, or the FBD, of these two gears. So there is a force exchange between the teeth that you might show them here with W23 or 32. They are the same thing, equal and opposite, based on the third law of Newton. And the angle of them with respect to the horizontal axis here is phi, the pressure angle, which for gears is typically chosen like 20, 22 and a half, 25 degrees or something like that. And it's a fixed angle. And these are the torques on the two gears. Typically, one of them is the torque that is applied through like a motor. So one of them is like the driving gear, and the other one is a driven gear. And this T torque is like generated on that. It's not like an external one. So it's not really correct to show this T. If you are showing free body diagrams, only one of the T's should be shown. And then, of course, the reactions of the pins, right, or the bearings, which in this case is like a two-dimensional force, an X component and a Y component, that the goal of it is to cancel this force between the gears so the center of the gears don't move. Okay, so this WB3 and A2 are the pin reactions, or the bearing reactions. And again, it's not really correct to show both torques, just one of them. Now, let's focus on one of these gears. Let's say gear 2. So if you look at gear 2, here we have decomposed the pin reaction and the force between the teeth, right, into horizontal and vertical components. We call here the horizontal component the tangential component, T, and the vertical component, we call them radial component, or R. Okay? Now, here is the first thing. By the way, D here is the diameter of the pitch circle. Okay, you know there are 4 circles on a gear. So when we say D here, we mean diameter of the pitch circle. So let me add it for you here. This is the pitch circle diameter. And as I said, it's not a good idea to have that. So now the first thing, if I want to transfer a power, so many kilowatts or so many horsepowers, between the two shafts, and assume that here I have 100% efficiency, so nothing is lost due to friction. It's never the case in reality, but for simplicity, let's say we neglect those frictions. In reality, there is always an efficiency for a gearbox that we have to multiply. But for the moment, let's say it's 100%. So the power here is shown by P in kilowatts. And N, as I said, is the revolution in RPM. So you can say that the tangential force, WT, that is applied on the gear is equal to 60,000 P over pi dN. And you might say, where did you get that one from? Well, you know that in general, power is what? Power is, in a rotary system, is torque times angular velocity omega, right? So this is the formula of power. And the omega here is in radians per second, but the formula I have, the parameter I have here for rotational velocity is RPM. So the relation between radians per second and RPM is omega equals 2 pi, because each revolution is 2 pi radians, n, and then divided by what? Divided by 60, and the reason is each minute is 60 seconds. So if I plug in here, you can see that power is equal to 2 pi over 2 pi and then n times t over 60. Correct? So from here, we can find torque. So torque is 60p over 2 pi n. And remember that the P that we have is in kilowatts, not watts. So since this guy is in kilowatts, I have to replace it with what? With basically 1,000 watts, right? Because this P here is in watts, but I want it in kilowatts. Remember again, this guy, this is standard unit. This is in watts in this formula, this guy. But what I have here is what? In 1,000 kilowatts. So I have to replace it by 1,000 times P, because that P is in kilowatts. So you will get what? 60,000 P over 2 pi n. And this is torque. And you know torque is equal to what? Torque is equal to the force, the tangential force in here, because you know it's only tangential force that creates a moment about center, not the radial force. The only force creating a torque is this Wt, so it's going to be equal to that Wt times radius, which is what? D over 2. And from here, you see that your Wt is going to be basically this formula that you can see over here. Look. That's the exact same thing if these 2's are canceled, right? So if you cancel that 2 with that 2 and bring that d in the denominator, 60,000 pi over pi nd, look, that's this formula over there. Okay, so this is how you get what? This is how you get the tangential force that is exchanged as a result of that much of power and that much of RPM. Good. Now, remember that the torque was what? The tangential force times the radius. We know that. Good. What else do we need to know before we go to the rest of it? Another thing that might be useful, not right now, but might be useful later, is the radial force. If somebody says, how much is the radial force? Then the radial force here, you can see that. Remember, this angle is what? This angle is phi. So you can see that tangent of phi, use a little bit nicer, tangent of phi is what? Is the radial component over what? Over the tangential component. So from here, radial component is tangent phi times tangential component, and that's what you can see over here. Now, what's the use of this WR, by the way? What does it do, really? Let's not say what the use of, what does it do? Because the tangential one creates torque. What does radial do? Radial will basically presses the gears against their bearings. It keeps the gears in place. Okay, and also, of course, it puts pressure on the bearings. It puts pressure on the bearings. So if you want to basically want to select bearings, which is another video, and I will talk about it, then this radial force is very important. So for now, let's just focus on WT, okay, which is important for gear design. Now that I have WT, how do I go about determining whether the tooth is going to tolerate this tangential force or not? What's the effect of this tangential force on the tooth in the first place? Well, you know that if you look at the profile of a tooth, this WT is going to bend the tooth, right? So clearly see it's a shear force And not only it can create some shear, but the main effect of it is bending. And WR also is going to create compression. So really, if you want to do very accurate gear design, you need to take into account WR as well as the effect of shear of WT on any cross section. But here in the equation we're going to see, which is called Lewis bending equation, which is typically used in gear design or gear selection, we neglect this radial component, assuming that this is small. And the reason is for this angle, pressure angle. As I said, this pressure angle, we typically go with something like 20 degrees or so. And tangent of 20 degrees is not very large. So the radial component is typically much smaller than the tangential component. So here we say that the bending stress is much bigger than this compressive stress. So if we just focus on the effect of WT, which is bending, then you see that this tooth of a gear is exactly like a what? Like a cantilevered beam that is subjected to what? To a force that is going to bend it like this. Correct? So it's going to go like that. So we're going to use the bending formula, M over IC, to find the maximum bending stress. And here some parameters come into play. First of all is the moment. The moment here is taken with respect to which point. Since we want maximum stress, we need to find the maximum moment. And for a gear, the maximum moment is with respect to this base of the gear here at this point A, at this cross section. Okay, at this cross section, that is like the maximum moment, and the moment is going to be that force times this distance L, this height basically, okay, which is like a working depth basically. So you need to multiply those two together to get the bending moment. And then I and C here, if we say this cross section is like a triangular cross section at that point, then this cross section at this point, it has some width and some depth. The width of it is considered to be T, and the depth of it is considered to be F. So the letter F is like the width of the tooth, and this is like the side to side. So this is like the tooth, let's call it depth actually. This is like the tooth depth. Right, this is how thick this tooth is. So if this gear is like that, correct? Let me clean up some stuff. If this is like this, basically, this F is basically that depth. Okay, so if that's a rectangular cross section, then I over C is going to be FT squared. This I over C, you can show that it's FT squared over 6, because I itself is really FT cubed over 12, and C is T over 2. Therefore, I over C, the S, the module, the section module, is going to be FT squared over 6. You plug it here, that 6 goes to numerator, and this is going to be your formula, this guy here. Okay, so this is the maximum bending moment. Now, clearly the bending moment is maximum with respect to this bottom section, but another thing you have to consider is, you might say, what about here? Why don't we consider that cross section? Because clearly the section here is smaller than that bottom, that's right, but the bending moment is much smaller too. So when they calculated the ratio of this bending moment and that I over C, they found that at this bottom, the root of the tooth, that's where you have the maximum bending. So this is where they are calculating the sigma max. Now, you can rewrite this formula, you can rewrite it in this format, W transpose PF over Fy. You see W and T are the same thing, the same W and T. This part is intact. The new part that is added is P and Y. P and Y are added. Let me use a different color. So this portion is new. And what is P and what is Y? You can mathematically show that these two are equivalent of each other. They are equal, okay? I'm not going to go about that because that is going to waste a bunch of time, but you can look at the textbook Shigley and you'll find Y. So here, this P is diametral pitch. This P is what? This is the diametral pitch, P, which is equal to 1 over gear modulus, and is equal to the number of teeth divided by the diameter of the pitch circle. Okay, so that's P. And this Y here, that depends on the tooth, we call it the, as you can see in this one, we call it the Lewis form factor. So this Y, this guy here, we call it Lewis form factor. And this is a function of the number of teeth. And you can find it in tables like this. So here you have the number of teeth and you have the form factor, the Lewis form factor. So once you pick a gear, you can find, based on the number of teeth, you can find Y. And of course, you can select, you can calculate diametral pitch. If you have selected the width, you can have F. You have the force from this top equation. And here you can find what? The maximum normal stress in the whole what? In the whole gear. Okay? So fine, I found the sigma max. Now what? Now, of course, you can compare the sigma max, again, the strength of the material, and come up with the safety factor, whether this tooth is gonna break under bending. As I said, if you want to be very accurate, you have to calculate the shear effect of WT as well as what? The compressive effect of WR. Okay? You have to calculate all of them as well as the bending effect. So it's a combined loading. But here we assume that those effects are much smaller than the bending stress. So we just focus on the bending stress. And because we neglected some stuff, we make sure the safety factor we choose is reasonable and definitely quite a bit bigger than 1. So nothing is going to fail. Now, another thing that is important, and this one you typically don't want to neglect, is the dynamic effect or dynamics effect. What is this? Well, when two teeth are basically working together, they are meshed together and they are transferring power from one shaft to the other, not only they are subjected to this WR and WT, they hit each other. There is impact, right? Because there is always some backlash in the teeth and there is always a gap. So when you have one tooth like that and the meshing tooth is like this, there is always this gap. So when they come and mesh together, there is always some impact here due to backlash. And the faster they rotate, this impact is going to be harder, and that is going to create more dynamic stress. So to consider that effect, the people who derived the equation here, which is a modified version of the Lewis equation, all they added was they added a dynamic basically coefficient, a modification coefficient, kV, which accounts for the speed of the rotations of the gears, okay? So the faster they rotate, the bigger this kV, so the bigger the maximum stress. Okay, now this kV is calculated how? So this kV, as I said, depends on how fast the gears are spinning. It's a function of V, and V is called the pitch line velocity, which is clearly what? Clearly d over 2 times omega. Or if you want to write it in terms of n, right? Remember, this is 2 pi over 60. So if you write it 2 pi over 60 n, that 2 pi and that 2 will cancel out. you will get what? You will get dn pi over 60. Okay, so you can do it like that. This is called the pitch line velocity. The bigger the n, the bigger the v, and we can see that the bigger is going to be kv. Now, what relation exists between kv and v? It depends on how the gear is made and from what material, but mostly it's a function of manufacturing. So you can see that, for example, for in the metric system, in the SI system, if the gear is basically, the profile of it is a cast profile, right? Then kV can come from this linear function. If the profile is cut or milled, use the milling machine to create the profile, then this is the function to go. If you used a gear hub, right, then it's this square root function. And if you use the gear shaver, then it's this guy here, which is kind of like the fourth root of v. Okay, so depending on the mode of manufacturing for the tooth profile, this kV is a different function. And so you can use this formula, which is the Lewis equation modified for dynamics effect. You can use that. And so a simple gear design without fatigue, you make sure that the maximum shear stress, Sy, over the sigma max is what? Is your safety factor, and this guy should be definitely bigger than what? Bigger than 1. So one of the parameters that you clearly see very important in it is this guy, F. So if this maximum load is too much, right, and safety factor is not more than 1, one of the best ways to reduce it is to what? Is to use a thicker gear, right? If you make this total depth, this F, bigger, clearly in an inversely proportional manner, sigma is gonna drop. Of course, it depends on how much room you have, but clearly you see you can make the gear thicker to reduce that total stress. So this is a simple what? A simple, or you might say it's not really simple. This is the way to go about static analysis of the gear tooth, whether the design that we chose is going to tolerate the load and it's going to pass the horsepower P at RPM N, or it's going to fail. Again, this is all static analysis, no fatigue. But is that it? No, there is one extra thing that you need to consider in order to make sure that the gear tooth does not fail. So not only they should not bend, but also these two teeth, when they are in contact with each other, as you know, they pass what kind of forces to each other? They pass this force W to 3. They pass this total force W on each other, right? So there is this tooth here, and there is this tooth like that, and they exchange this force W. Or the basically the tangential form of it, WT. They are passing these forces together, where WT is clearly what? Clearly this is W times cosine of the pressure angle, right? So these two forces are now, these two surfaces are under what? Because these W's are pushing them, they are under compression, right? They are under compressive surface stresses. So are they going to tolerate these what? Are they going to tolerate this compressive force on their surfaces, or are the surfaces of these teeth start to what? Start to deform. So after a while, your teeth is going to look like this, right? Or maybe this one. So are the teeth are going to, now this is of course with the exaggeration, but are these teeth going to tolerate the amount of compressive force, which we might also call Hertzian force, right? Or are they not going to do it? So here, the model that is used for this formula is two cylinders on the top of each other, where the force exchange between them is like WT, or W in general, W, let's call it. And here, the Hertzian force between two cylinders, where the radii are R1 and R2, the radii of curvature of them R1, R2. The Hertz stress between these two cylinders are calculated based on this top formula. Okay, now in our case, we know the teeth are not cylindrical surfaces, they are involute surfaces. So it's just an approximation. It's not perfect, but it's a good approximation. And let me explain everything in this formula for you, so you have a better understanding on what we are dealing with in this formula, or how to go about calculating it. So the first thing you see is W tangential over cosine phi. Well, what is that? Remember, from here, I said that your WT is W over cosine phi. So what is W from here? W is WT over what? Over cosine of phi. So whenever you see that, that is what? That is the total force exchange between the two surfaces. Okay, so that is your total force W. The kV is still there, the modification for dynamic effect. The depth of the tooth still there. Here you have this 1 over R1 and 1 over R2, where R1 and R2 are the radius of curvature of the teeth, of the surfaces of the teeth, these guys. Now, of course, I'm not the best at drawing these profiles. Let me do a better job this time. So something like this. So at this contact point, if there is a radius of curvature here, like this maybe, this is like R. So for one gear is R1, for the other gear is R2, radius of curvature of the involute profile at the contact point is R. By the way, how do you calculate R's? You can show that R's are the diameters of the pitch circle over 2 times sine of the pressure angle. Okay? Geometrically, you can show that. Again, my goal is not to prove that. So here you plug in this R1 and R2 in this formula, W2 kV cosine phi f, everything is there. Take a square root, multiply by a CP, a coefficient which we call elastic coefficient, and with a negative sign. Negative is because this stress is compressive stress. So now what is this elastic coefficient? It's clearly a function of the elastic properties of the two teeth. So as you can see, it's a function of the Young modulus of the two teeth, E of pinion and E of gear, and their Poisson's ratios, nu of P and nu of G. So if you calculate the CP, plug into this formula, you get this maximum compressive or Hertzian stress. And again, this guy should not be more than the maximum compressive stress those materials can what? Can handle. So if the maximum compressive stress of the material divided by the sigma C, which is like the other safety factor, you might call it safety factor number 2, if this guy is also bigger than 1, then the surfaces will not deform. And as I said, if this one, which you might call safety factor 1, is bigger than 1, then what? You can ensure that the teeth are not going to bend. Now, of course, here, as I said, you want to go quite bigger than 1 because we have been neglecting the effect of this WR. But in general, if we use the Lewis equation and this Hertz stress equation, we can make sure our teeth, the teeth of the gear, will work to pass the power P between the two shafts, while the RPMs are N1 and N2. So hopefully this video was useful to you, and I will see you in the next lecture. Thank you.